is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hello and welcome to SkyTour Radio here on KGRAradio.com. I'm your host, Mark D'Antonio, here with my increíble co-host, Amanda Curran. Hey there, Amanda. How are you?
Hi, Mark. I'm well. How are you?
Fine, thank you. And let's welcome our KGRA listeners to the broadcast. Hi, everybody.
Hey, y'all.
So I have a couple of announcements first. SkyTour live stream on our YouTube site. We have two new videos. One of them is one that Amanda created. It's called the SkyTour News for February 11th. And that's, of course, one of Amanda's creations. She does a wonderful job with it. And on the SkyTour live stream site, I put up a video earlier today, actually a little while ago, called it's called SkyTour Live Streams Science of the Universe. And it celebrates our 8 months of SkyTour live stream, and it goes through all the many objects we saw, and it gives you details about them. So check it out. Hang out there and have fun. Make sure you subscribe also to SkyTour live stream and the YouTube channel, and don't forget to click that bell to get notified when any of our events are happening, be it a new SkyTour news or a new SkyTour live stream that might be starting. Lastly, our online store at fxmodels.com or at the Planetary Replicas page on Facebook, the FX Models Planetary Replicas page. If you're looking for Moon, Mars, or Pluto swag, head there, okay? And you can find out if you are eligible for a $15 discount by entering ST15. That is ST15. That's the purchase code for today. And if you enter that code, you'll get $15 off on your checkout at the store. Now, the links are on the SkyTour radio page as well at KGRAradio.com. So tonight on SkyTour Radio, do you know what we're going to talk about, Amanda?
I do.
Why don't you tell everybody? Go ahead.
We're going to be talking about the formation of stars.
That's right. And you're going to share how much you're going to basically bring us on that tour, aren't you?
Oh, sure.
I'm kidding. Now, we wanted to talk about this because this was something that's crucial to understanding the universe. And, when you're a nerd or a geek like me, this is the kind of stuff that keeps you awake at night. And if you watch my video that I put together up there on the SkyTour Science, you'll see what I mean. So when we go into star formation, I think the first thing that we want to do is we want to talk about really just the basics. How do stars form? Well, they form from the most abundant atom in the universe, and that atom is hydrogen. Now, at the beginning of the universe, when the Big Bang occurred, the amount of hydrogen that was created was just stupendous. But there was also small amounts of lithium, beryllium, and helium that was created at the same time. And so that was sort of the basic elements within the universe at that moment in time. And when a star forms, we find that there are clumps of hydrogen gas in the universe, both in the early universe and in the current universe. And that means that the universe wasn't very symmetric in the way it expanded. There was clumping going on. This is good because without clumping, we wouldn't be here. If everything was all the same, then there would probably be nothing to spark the collapse of one particular area versus another, and thus clouds of gas that might be denser over here may not occur. And that's something we absolutely need. So when we had clouds of hydrogen gas and other trace elements in the early universe, and even now, they would collapse under their own gravity as soon as they were isolated enough through whatever disturbances from nearby stars or other things that might cause them to move and move the gas moving around in space. And when it collapsed, some of these hydrogen atoms would form hydrogen with another hydrogen atom, making a molecule of hydrogen. So H2, like H2O, but without the O, without the oxygen for water. And these H2 molecules would form by the trillions, and they're all over the place. And we call those molecular clouds. And we'll talk about that later, because molecular clouds are very important for life for us or extraterrestrial life. It's very important. So here's what happens when a cloud gets denser, from the mutual gravitational collapse. All right, the temperature will increase inside that cloud. The density, of course, increases, but also the pressure increases. So you have to imagine that a cloud that's collapsing, it's getting hotter, it's falling under higher pressure in the core, and at a certain point, all those hydrogen atoms in there are going to get pushed past a certain level, and that certain level is around 100 million degrees. And that starts something called nuclear fusion. Now, the fusion process is very complex, but overall, it means two hydrogen atoms will combine to form a helium atom. It's the power plant of the stars. We're trying to perfect that now. And in my book, The Populated Universe, I discuss the concept of fusion, and I discuss how we're always seemingly 10 years away from the break-even point where we put in as much energy as we get out from a reaction. And there were some rumors recently about us getting more out than we put in, but those were sort of unsubstantiated, couldn't be proven nor repeated, which is sort of the most important thing. If you can't repeat it, then it's not good science yet. So this is the process that powers the sun. It's the process that we'd love to use for power because pretty much it means unlimited power for us. And these hydrogen atoms will combine to form a new atom, helium. Now, when that happens in a star, and that 100 million degree flashpoint happens in the core of this cloud, and the star begins to fuse and burn, okay, that helium that's making stays in the core of the star because it's hydrogen mostly in the cloud of gas, and then the helium is in that core. So here's what happens with a star, and this is why they're so amazing. They're in a constant battle. Gravity's trying to win out and collapse them at the same time that their outward pressure from the radiation they're generating is balanced by this gravitational collapse. That balance is called hydrostatic equilibrium, and it's something that we have to consider when we talk about stars. Now, we have to say, okay, what are stars good for? Besides providing warmth and radiation, okay, if you recall any of your high school chemistry, any of you out there, well, stars help populate the periodic table of the elements. In fact, stars are responsible for the periodic table of the elements, aren't they? Right? Did you know that, Amanda? I think you did, didn't you?
I did. And I had a question, but I'm so scared to ask questions because I don't want to derail where you're going.
You're not going to derail it if it has to do with atoms and the periodic table. It's perfect time.
Well, okay, all of these elements everywhere in the universe,
yep,
were all created at the time of the Big Bang, correct?
No.
Yeah.
Now see that doesn't derail me. That's actually good to know that if you think that, then there's other people that are going to think that. This is not a bad thing.
Or it only had one thing, like it only had hydrogen, and then it in turn eventually turned into helium and so on and so forth. But I mean, it's such a big question. I can't say, what exactly was given out at the time of the Big Bang, because do we know? I doubt it. I don't know. I keep going back, why until we just don't know yet,
That's okay, because all of our theoretical work shows us that hydrogen was made, lithium, beryllium, and a little bit of helium. All right? That is what was made at the Big Bang. All the other elements were manufactured later in the stars. Now, you remember the periodic table, of course, right? It's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. And you know this, and I'll say it, but I'm not going to do it. I can sing the whole periodic table. I know the whole periodic table, all the way 118 elements and everything. I know them all. Why? I don't know. Maybe I don't have a life, but I do remember. I actually had to memorize whole groups within the periodic table in chemistry class, and it really made it easier. But then when it came time to learn the atoms in the periodic table, I learned more about how they came about, how they derive from each other, and at times then I discovered that, wow, there's a lot of connections here. There's a lot of stuff here. You can actually figure out what comes next in the periodic table. All right. And that's kind of what atomic physicists do, every day. It's like, hey, Bob, I got another element. I got another element over here. Hey, cool. Let's see. It's highly radioactive, or whatever. But, we know that we have 118 elements in our current periodic table. But numbers 95 through 118 are all synthesized in the lab. Now, what's that leave? It leaves 94 of them that aren't synthesized in the lab. Where do they come from? Well, we're going to find out. So the first thing we want to do is ask, what is an element? Well, an element is an atom. And what's an atom? Well, we all know that, most of us, an atom is composed of these elementary particles, right? Protons, neutrons, electrons, and so on. Okay, you can go very detailed on this and go into what the protons are made of, what the electrons and neutrons are made of, and so forth, and go down that whole path. But we're not going to do that. But why do I mention this stuff about the atoms? And it's because stars make these new atoms in their cores through the hydrogen fusion process and through the fusion process all the way down the periodic table. What does that mean? Well, let's start with a simple one. Hydrogen fusion takes two hydrogens and turns it into one helium. Now, the process liberates a tremendous amount of energy when it does that. This powers the star, and that's why stars are bright and live for billions of years, because there's plenty of hydrogen from which they can generate energy. So in a chemistry sense, that's the hydrogen atom, which is one proton and one electron, plus another hydrogen, which is another proton and another electron, under heat and pressure, yield two protons and two electrons, or a helium atom. So it's very simplified, but those are the basics. Now, again, they're being squished together and smashed together under high pressure. Pressures we can't even imagine, actually. So stars make elements this way, and this is how hydrogen to helium is made, all right, in a star like our sun. But in other stars, you can make more elements down the periodic table, as we'll see. But later, when these stars die, they also leave behind these new elements that they've forged in their cores. And in that process of dying, they also create new ones in the process. All right. Now, new stars, like when our sun formed 4.6 billion years ago, there were already plenty of elements in the interstellar medium. We call it the ISM, the interstellar medium. And it was enriched by all these previously made elements in the cores of other stars. So our sun has elements that are in its atmosphere that we can see in its spectrum when we break out its light into all the rainbow of colors and see these lines in there that indicate different elements. The sun has these elements that it cannot create in its atmosphere. It's not massive enough, for instance, to create calcium. It's not massive enough to create magnesium. But it has lines for these. So you say, well, where did those come from? It was formed with those. It started with those. See, because it came from a mass of hydrogen plus this calcium, this magnesium, these other elements. And the sun has a specific spectrum that we actually call a Fraunhofer spectrum. It's a well-known bunch of lines that correspond to atoms that are making energy transitions up and down within the atom. And those lines that we see are in characteristic places in the spectrum of a star. And that's how we identify what stars are, what types of chemistry they have going on in there. And so a star like the sun can make helium, maybe some carbon, okay, and potentially a little oxygen, okay, because of the mass. You have to have a massive star to make more than that. If you look at the periodic table, you'll see that that's not too far down into the periodic table. Not only that, massive stars, the stars that are much heavier than the sun, okay, maybe 8 to 15 times the mass of the sun, these guys can make only up to about iron in the periodic table, which is only number 26. So, but wait a minute, 26 to 94, that's left over. Where do those elements come from? You see, so there's a lot that we have to go through here to figure this out, and we actually do know. Now, for those heavier elements beyond iron, a supernova, that is when a massive star destroys itself, a supernova will create many more of these elements. Now, from research in the last couple of years, we now know that merging neutron stars can also create certain elements that we didn't realize, like gold. Okay. Now, so up to element 94 is created in the stars, and the rest are lab synthetics, that are created in the lab. Now, when we look at stars, stars live for as few as 100 million years to trillions of years. And it really depends on their temperature and on their mass. All right. When we talked about the stars from the "Oh, be a fine girl, kiss me" metaphor that we had last year, the OBAFGKM, and you said "Oh, be a fine guy," right, Amanda? You remember that one? Okay. That moniker, that little metaphor that we used, those O stars, if you recall, were the hottest and the brightest and usually the biggest mass, and that also meant the shortest lived. Okay. And these O stars like that are going to be the shortest lived stars. All right. And they're always going to explode in a massive giant supernova. Okay. And then the other end of the spectrum, down by the lowly M star, all right, they're very red, very cool stars. These M stars, they only burn at about, and their surface temperature is only 3,000 degrees or so, and that's Kelvin degrees. At that temperature, the star can live for trillions of years. And that's just what extraterrestrial life requires. Stable star, long times, all right? That's exactly what these stars offer. So it's very likely, and because the M stars are the most actually populous star in our entire galaxy and probably other galaxies, most likely the M stars, of course, will have the most planets. And because the M stars last a good long time, there's many chances for life to occur on one of these M stars, around an M star, on a planet around the M star. This is why I think that this is really such a good thing, because when we look at these different stars, we can't even see an M star when we go out at night. Remember, we talked about that last time. Now a star like our sun, which is a G-type star, it lives about 10.
I was just about to ask you that. For some reason, G was sticking out in my head, and I thought our sun was G.
It is very good.
Yay.
It's a G2, all right, and it lives about 10 billion years. And now, but here's the thing: once the primary fuel, which is hydrogen, once that primary fuel is used up, all right, in a star like that, then that outward pressure. Remember, I talked about the hydrostatic equilibrium. The star is always in a war between the forces trying to collapse it and the outward pressure trying to hold it up. Well, if its fuel starts to falter, gravity begins to win, and the star will start to collapse. All right, and say once that primary fusion, most of the hydrogen is used up, once that stops or slows down, then the star is going to start to contract and collapse again. All right. And now as it does that, it gets hotter in the core. And guess what that does? That allows more fusion to begin, this time in shells around the core that previously weren't as hot and couldn't do that nuclear fusion. Now they can. And so now we're getting hydrogen fusing in the area around the core of the star rather than in the core only, because this is now a hotter area. So, maybe helium and carbon and oxygen can be made in some shells around the outside. But when that happens, the star swells up with this renewed temporary energy and becomes something we call a red giant. And that's the sun's fate. All right. When it uses up its primary fuel, it's going to start to collapse. Hydrogen in those outer shells will start to fuse now, whereas it couldn't before. And boom, the star swells up much bigger. And with that renewed temporary energy, it'll be very, very large. In fact, it'll most certainly swallow Mercury, Venus, and likely the Earth. So we better get out of here, folks. We're going to have to make sure that we figure out a way off of this rock. Okay, otherwise it's only going to be a rock or a burned cinder at that. So, and we say red giant, by the way. Why red? Why not green giant? Why not blue giant? The answer is that as the star swells in size, those outer layers are farther from the core. Those outer layers aren't doing fusion. It's the inner part of the star that's doing fusion, and that heat is getting transferred to the outside. Well, as the star bloats like that and swells, the temperature gets lower. And we know that in stars, the hottest temperature is blue and the coolest temperature is red. So as the sun begins to cool, as it swells into a red giant, it will start to become redder and redder. All right. So it'll be a permanent sunset all day long. Okay. Except it's going to be getting a lot bigger on the on our horizon as it rises and sets. So now, this other thing that happens when the star becomes a red giant is sometimes it's a turbulent time for these stars, and they will pop. They'll actually puff a little bit. They'll puff out, and when that happens, they can actually throw off some of their outer layers. All right, and these outer layers just keep going because they're so far from the star that they're not even gravitationally bound anymore. So the slightest effort at all to push them out from some radiative pressure whatsoever can knock them off, and this becomes a nebula around the star core. All right, and the star core itself continues to collapse. All right, and in a star like the sun, it's going to become something called a white dwarf. Now, you know what a white dwarf is, right? Remember, we've seen several white dwarfs in SkyTour live stream. Do you remember them, Amanda?
Not offhand.
Okay.
I remember you talking about the nebulas.
Yes.
That's all starting to come back to me. And you have to keep in mind, this is all basically new information. I'm starting to remember bits and pieces now, but bear with me.
Oh, no, that's fine. I know I'm putting you on the spot, but you know, it's kind of fun because I'm trying to actually.
Well, for some, maybe.
Well, no, it's fine. It'll be fine for you too. Because my point is, when we talk about a white dwarf, you know, we don't really see. Well, okay, it's a white dwarf. What's a white dwarf? A white dwarf's the end state for a star like our sun. Now, the way it works is really strange. When the core starts to collapse in these stars, because there's no more radiation pressing outward, well, the mass only allows a certain amount of collapse, and then it stops. Now you would think, well, why should it stop? Well, it stops because the matter becomes something called degenerate matter. Now, it doesn't mean that it's like on the wrong side of the tracks and doing foul, bad things. Okay, it's not doing that. It means that the electrons in these atoms are so packed that there's no room for any others at any other energy. Okay, and it relates to something called the Pauli exclusion principle, but don't worry about that. It causes, though, an outward pressure that prevents further collapse for stars that are about the mass of the sun. Okay, so it's like saying the room is full, no one else can enter. They're all, shoulder to shoulder. You can't get another person in there. All right. So that's what will happen with our sun. It's going to go to a white dwarf, but because those electrons are so packed at the surface, because the atoms are so dense, that it actually creates an outward pressure, and it's called electron degeneracy pressure, if you want the term. And that degeneracy pressure prevents that white dwarf from collapsing further. Okay, again, only for stars about the mass of the sun. So for stars like our sun, the white dwarf surface is going to be mostly carbon and oxygen atom, and that's why they're called carbon oxygen white dwarfs. And this degenerate matter is oddly in a very stable condition. Now, to get an idea of what we talk about with this, a teaspoon of this matter here on Earth would weigh 15 tons. A teaspoon. Okay, I mean that gives you an idea of how compressed this white dwarf is. And by the way, a white dwarf is about the size of the Earth, maybe a little slightly bigger, slightly smaller, depends on the star. Okay, so excuse me. What about the envelope of the star that got sloughed off that we talked about before? That sloughed off envelope, okay, that is something else. All right, and that sloughed off stuff is actually something interesting because that we call a planetary nebula. Now in SkyTour Livestream, we've seen a few of them, and things like the Dumbbell Nebula, the Ring Nebula, and in these you can actually see the little white dwarf right in the center. So they're very luminous stars, even though they're tiny. It's because they're so highly energetic. All right, so they're called planetary nebulae. The sloughed off stuff being caused to glow by that white dwarf, because of the fact that they could be confused as a planet, not by us, but by people in the 1700s, 1600s who are looking at these things They call them planetary nebulae. Charles Messier, when he put together the Messier catalog, okay, he called them planetary nebulae as well. But they're not related to planets. But we didn't know anything about them back then. No one did, so they didn't know what to call them. So the planetary nebulae will release all that stuff, all the elements that they made in the star, in that envelope, are being released back to the interstellar medium. And a star like the sun could probably make up to helium, perhaps carbon. But the heavier elements are going to require a more massive star. And so that is something that's interesting. And when we come back from the break in a bit here, we're going to talk about higher mass stars. And we're going to see just how the higher mass stars are really an oddball and really strange. So what do you think of that, Amanda? This is all coming back now, isn't it?
It is, but okay, my next question is, when you said the envelopes were sloughing off, they would be cooler, you mentioned the dumbbell and the ring, and they're both blue, which would suggest that they were hot.
Except,
so
you're right.
What am I missing?
That's very good. That's such a good question. I'll tell you why. Because they're not cool. They're actually very, very hot because of the fact that the white dwarf in the center is highly ultraviolet rich. It has an ultraviolet energy. And we'll talk more about that when we come back. I'm Mark D'Antonio on SkyTour Livestream here with Amanda, and we'll see you in just a bit on KGRA.
This is SkyTour News for February 11th. I'm Amanda Curran. Today in 1952, Collier issues Man Will Conquer Space Soon. Collier's magazine first published papers from the first symposium on spaceflight under the title Man Will Conquer Space Soon, detailing Wernher von Braun's plans for manned spaceflight. Individual articles were authored by such space notables of the time, such as Willy Ley, Fred Lawrence Whipple, and von Braun himself, and contain some of the finest magazine illustrators of the time. The article series was the basis for 3 episodes in the Disneyland anthology series Man in Space, Man in the Moon, and Mars and Beyond, and the series was expanded into 3 books, Across the Space Frontier in 1952, Conquest of the Moon in 1953, and The Exploration of Mars in 1956. Today in 1992, the JERS-1 was launched. The Japanese research satellite 1 was sent into orbit to verify functions and performance of optical sensors. It carried with it an L-band, HH polarization, synthetic aperture radar, a nadar pointing optical camera, and a side-looking optical camera. It established an integrated system for observing the Earth's resources, to perform observations and measurements for land survey and agricultural as well as environmental preservations, disaster prevention, and coastal surveillance. The satellite operated until 1998 and re-entered the Earth's atmosphere in 2001. Today in 1995, Discovery returns home. After completing its 12th flight to space, Discovery returns from a rendezvous with the Mir space station. Once described as a dance in the cosmos, Discovery closed the 4,000-mile gap to 400 feet, getting as close as 35 feet to the station in a dress rehearsal for future missions before it returned home. In addition to testing the systems and techniques required to rendezvous with Mir, the crew was also able to retrieve the Spartan 204 satellite, which obtained data on UV light that reflected off the shuttle and into space. This is SkyTour News. I'm Amanda Curran.
Hey Hey, welcome back. This is Mark D'Antonio with SkyTour Radio with Amanda. Hello, Amanda.
Hello, Mark.
There she is. And we had a question before we broke. Actually, it came from Amanda. She was asking why, if those sloughed off layers from a star are supposed to be cooler, then why are we seeing green and blue in these things? It should be red, because blue means hot in terms of stars, right? Well, actually, what we're looking at is something else that's going on there. The white dwarf that's at the center of these dying stars, these dead cores that are sitting in the center there, are anything but cold. They're very hot with ultraviolet energy in the exposed core, and that ultraviolet energy radiates out and hits the elements that are out there in that envelope that got sloughed off. And when they hit those atoms out there in that envelope, what they do is they ionize them. And by ionizing, I mean they take their electrons and force them off the atom. And when they go through something called recombination, that is, the electrons recombine with the atom, all right, because as they bump around, they lose energy and they recombine with the atoms. When they do that, they give off a characteristic color. And depending on the element, that color can be different. So in some of these planetary nebulae that look blue, we're seeing a lot of oxygen, because oxygen is characteristically blue when there's that recombination going on. If it's red, then hydrogen is what we see, because the recombination is giving off something near hydrogen alpha, which is, I think, 63 angstroms, or 656 nanometers. Not to worry, but I'm close. But when we see this stuff happening, we can identify the elements that are in these envelopes that were sloughed off of these stars. And that's how we do it, by examining the spectra of those elements directly this way. So this is very cool. And I'm glad you asked that question, Amanda. Thank you. That's a very, very good question.
Well, I get confused easily, so I want to stay on top of things here.
No, but you know what? That's okay. All you have to do is ask a question, and confusion will go away. Now,
It tends to.
yeah. So we talked about planetary nebulae, which occur with stars around the size of the sun, slightly larger and smaller. Well, what about higher mass stars? They suffer definitely a different fate. Planetary nebulae, all right, are gentle, easy ways to go. Yay, it just sloughs off and kind of goes away, and the star collapses to a white dwarf. Nothing violent happens whatsoever. Well, the high mass star is just a little different. When you talk about a high mass star, you have to consider that those stars, they tend to pulsate, all right? And as they grow and shrink during their evolution, more massive elements can be made in their cores and in the shells surrounding the core. And a larger star will have many shells fusing elements around the outside core. You can have hydrogen going to helium, like we're familiar with, helium going to carbon, carbon going to neon, neon going to oxygen, oxygen going to silicon, and silicon going to iron. All right, all in these shells where iron is in the core, iron, nickel in the core. So iron is at 26. It's actually an isotope, iron 56, that is the farthest it can go. And finally, when it reaches this iron, it can't fuse anymore beyond iron. Now, why is that? It's actually pretty simple. Iron needs more energy to fuse than it gives back. So a star can't put in more energy than it has to fuse iron, because it won't get it back. So that said, iron sits like, I don't know, something stuck in the throat of the star. And the star can't support that for a long time. So what happens is, once all the fusion is burned in all the shells surrounding the core, which is iron, in these heavy stars, these massive stars, then once the fusion slows down and wanes, gravity begins to win. And as it collapses, it becomes like a runaway. And what happens is, it's a catastrophic core collapse. And it happens within a quarter of a second for these stars that are massive, far beyond the sun in size. And this outer core will bounce off the inner core. And the result is that it blows all the outer layers away from the star in a massive explosion that's the biggest thing that the universe has to offer, besides the Big Bang and a hypernova. So We'll talk about hypernovas another time. But excuse me. Um, in a supernova, massive pressures and temperatures are at play, and what happens is that literally blows right past the pressure that a white dwarf might exert, all right, on that core. Uh, when a white dwarf, remember, it's stable and it has that pressure that's pushing back, which doesn't allow it to be collapsed further or pressed further. Well, a massive star can blow right through that, but it leaves behind something, not a white dwarf, but leaves behind a neutron star. But like white dwarfs, neutron stars are also in a state of what we call degeneracy, and we have neutron degeneracy going on the surface of a neutron star. And as before with the white dwarfs, and also the same with a neutron star, the outward pressure from those packed neutrons is such that it prevents further collapse for certain stars up to a certain mass above the suns. But the time that, if you want to consider the amount of weight on the Earth that such a teaspoon of that material would weigh, now instead of 15 tons like a white dwarf, a teaspoon of neutron star is up to 4 billion tons on the Earth. Isn't that, it's like, you can't even fathom that.
No.
We don't have anything that can hold that, right? Can you imagine that? I mean,
No, the numbers that big, I can't even compare it like logically. It's too over my head. But
well,
what kind of star would that be then? How much bigger than our sun? Like, what would an example be? Is Alpha Centauri that big?
No, Alpha Centauri is a star kind of like our sun, but some of the stars in Orion, like in Orion's belt, there's O stars in Orion's belt. Okay, Alnitak is an O star, and if you look at what happens, Alnitak is going to go supernova someday, and when it does, we're going to have a front row seat because we're in the galaxy kind of near Orion. All right, we're in something called the Orion Spur, so we actually have a front row seat to Orion, and when Alnitak goes supernova, it's going to leave behind a neutron star. All right, so it's a very high pressure situation and very high temperature situation. This is where all the rest of those elements come from, up to 94 that we were talking about, partially. Then we also have a situation where if you have a binary star where one goes supernova, the other goes supernova, leaving two neutron stars behind, well, then maybe those neutron stars can merge at some point, and in that merge, there's another event which occurs, okay, and that recent one that we saw was called a kilonova, and that was a massive nova with a lot of temperature, a lot of pressure, and they discovered that in that kind of collision, a lot of gold was made. So the thought was, hey, maybe these types of collisions around the universe have caused the amount of gold that we see. Now, gold is a very heavy element, but it's also not very common in our crust. It's a very small amount. That's why, hence, it's so valuable. But when the Earth was molten, the gold that was in it started to settle toward the core of the planet in a process they call differentiation. Okay, and so some of it didn't get all the way down. Some of it's still in the crust, and we can get at that. But some of it, like I said, was made in these merging neutron stars. But guess what? We can go even higher mass. What about very high mass stars? Okay, where the core of the star alone, the core of the star, is bigger than 2.4 suns in mass. Okay, and the sun's 864,000 miles across. Well, just imagine a core of the sun having as much core of that star having as much mass as 2.4 suns. When that happens, then the collapse of the core continues. It goes right past that white dwarf electron degeneracy level, it zooms right past neutron star degeneracy level, and goes right down to singularity. And what's that? It's a black hole. Yeah, and that's the universe's most malevolent creation. I got to tell you. I don't think now, if our sun went and turned into a black hole right this second, besides not knowing it for 8 minutes, because it takes 8 minutes for light to get here, we would also discover that nothing would change, because the black hole doesn't suddenly pull in everything that's in orbit. If it's in orbit, you're safe. If it's not in orbit, well then, good luck. You know, but everything could swirl into it at that point. If it's something that's very very massive, and not even light can escape its grasp, which is actually pretty cool. Now, the theory is that every galaxy, like our own, like the Andromeda Galaxy, has a supermassive black hole at the center. It's the ultimate universe gobbler. What do you think of that? Isn't that crazy?
I thought I heard maybe a year or two ago they thought they caught something escaping a black hole. I don't know. I don't remember the details now, but did you remember hearing anything about that? Something? They thought something had escaped? Yeah.
Yeah, that was actually, I believe, they noticed some intense magnetic fields. And technically, you shouldn't have expected to see those, but you can because the magnetic fields are occurring outside what's called the event horizon, where beyond which nothing can escape. And there's very, 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 very powerful magnetic fields at the horizon and just above. This is something that, people saying, oh, we'll use black holes for energy. Yeah, I don't think so. Okay, a starship powered by a black hole is a dead starship. Okay, that is a dead starship. But think about this. We have come so far in our astronomy knowledge from just say the 1800s, and I was out the other night and I wanted to do this because we have Valentine's Day coming up. And what I did was I actually took a picture that Amanda, you'll share it in chat, I think.
I'm on it right now. I think it's absolutely beautiful.
It's a nebula that I took. It's called the Heart Nebula. And with Valentine's Day coming up, I just wanted to give you all a moment. Okay? All right, now it's past. All right, back to business. I'm kidding.
It's gorgeous. It's absolutely gorgeous. It's in chat now, so hopefully people can check it out. It's beautiful.
Great, and I will I will put it up as well on the SkyTour live stream site, but it's also in the SkyTour live streams Science of the Universe video that I also uploaded just a little while ago on the SkyTour live stream website, okay, or the SkyTour live stream site for YouTube on channel on YouTube. Blah. So. Go there and check it out, and you can see the Heart Nebula in there as well. And then I'll put it up on SkyTour live stream for those of you who want to actually check it out. Now, I bring this up about the 1800s because I have a book in front of me that's falling apart. It was published in the 1800s, and it's called The Architecture of the Heavens in a Series of Letters to a Lady. And I think this is so appropriate for Valentine's Day because the book is arranged as a series of letters, all right? And these letters will describe to the quote-unquote lady the science of astronomy. Now, the terms being used are far beyond what ladies of the time could possibly understand unless they were also scientists. So what does that tell you? It tells you that...
People were sexist back then?
Well, besides being sexist back then, it also tells you that astronomy back then probably, and I know this for a fact, wasn't really accepted as a true pure science. Not like biology, for instance, where they could grab a specimen and what they do, they dissected it. Hey, okay, it tells us what it's made of, okay, how it's made. Okay, we can't dissect a star. We couldn't capture a star. In fact, they didn't even know what stars were. They didn't know what nebulae were. Like when you look at the Orion Nebula, we've seen the Orion Nebula in SkyTour live stream. It's 1,400 light years away. It's a star-forming region. We know that now. But back then, they said it was a cloud in the firmament. They had no idea what it really was. And they didn't know at all how far it was. But I want to just read some passages here. And I'll do my best because you have to understand, this is flowery language. Okay? I'm fighting a cold.
Because they were disguising it.
Yes, exactly so. They had very good. I'm glad you came up with that because I missed that point. They're disguising the science in flowery language to a lady because that's the only way this book would have got published.
Would that have been considered witchcraft almost at the time? Like,
no, it wouldn't be witchcraft.
Not that far, no.
No, but it would have been considered. I can tell you, it would have been treated like UFOs are treated today, by mainstream science.
So, like astrology.
Yeah, I mean, there are people that believe in astrology, and then for most people who look at astrology, they say, well, that doesn't really make sense to me. It doesn't. There's no scientific basis for that. But in this day, when they were writing about astronomy didn't have much factual basis other than what they could observe with their crude telescopes. And so they didn't have much else. But listen to this. This is letter 7, the nebular hypothesis. Now, I'm not going to read the whole thing. I'll just read a short paragraph just to give you an idea of how they wrote. This was not a textbook, but a popular book that was sent out to tell people about astronomy. And when I read it, I thought, Jesus, are we stupid or something? I mean, did we shrink back in our ability to understand the English language or something? Well, the fact is, no. What happens is they wrote it in this very flowery way in order to get past, the people that would otherwise say that you're just trying to teach astronomy, which you don't know anything about because we don't have any science about it that teaches us astronomy. So this is letter 7, the nebula hypothesis. I wonder if I should read it in that voice. What do you think? That would be annoying?
Yeah.
So I won't read it that way. Okay.
I thought that was like going to be the fuel to cement the idea.
Yeah, that's all right. Letter
7.
7. Let us note the exact amount of evidence constituted by the speculations of the foregoing letter on behalf of the daring hypothesis that all the existing stellar bodies sprung by virtue of the law of attraction from the bosom of a chaos of which stray specimens are still found in the heavens. Do you have any clue what he just said there? I don't. I mean, it's just like, it's crazy. All right, so anyway, insofar as this hypothesis undertakes to explain the nebulae, I do not conceive that much of an accessible knowledge is now wanting to confirm it. For the agreement of the forms of the nebular substance with the natural results of the persevering action of gravity seems almost demonstrated. Oof, wow. But it must not be forgotten that there is another correlative and very extensive inquiry which the truth has not touched. This hypothesis must also explain the stars. If it is the true cosmogony, and we have at length approached the right theory of the formation of things, we should indeed obtain from a satisfactory idea of the meaning of that curious progression of the structure which so strikingly characterizes the nebulous masses. But it is no less imperative that it exhibit with proper distinctness how the mass of stars around us, along with other peculiar features and arrangements, might have been involved in obedience to known mechanical laws by the condensation of nebula. I mean, what do you think of that?
I actually like it.
Anyone,
I do. I know.
For those that want to read this, I will have Amanda, or I will do it. I will post. This is a book. I have the actual book in my hands. You can hear the paper. Okay. I will have Amanda post the version of this book that's online. It's not The Architecture of the Heavens in a Series of Letters to a Lady. It's just called The Architecture of the Heavens. All right. By the same guy, J.P. Nickel. All right. And the book is really quite an amazing read. It's falling apart here because I did read it. Why? I don't know. Punishment? I don't know. I was so curious about what they thought. Now, the book has paper pages, of course, and then there's these plates where they have they're not photos, but they're prints that are covered with little tiny tissue paper covers that you might see in some of the old books. And the tissue paper covers were to prevent the ink from actually getting smudged by the reader. Really, really interesting,
Wow.
And the images they're all hand drawn.
By him, or who is the artist?
Yeah, well, by him, but they're not what you think. They're just black and white. All right, and like one of the images shows a successive number of stars. Okay, as seen through a telescope, and they have little discs around them and stuff, and it looks kind of like it was done with a pen and ink, and it was stippled. Really strange. So I don't know if anyone has any questions about that, but I'd be happy to listen.
No one, the people were enjoying it, said it sounded interesting, didn't really have any questions about it, but
Good.
no, but I mean,
See, he goes on to talk about the form of the zodiacal light, the form of nebulae. See, zodiacal light, okay, is something that you see early morning, okay, on just before sunrise, and it looks like a vertical column of light off the horizon. And what is that? Well, believe it or not, our solar system still has a lot of dust in it, all right, left over from the formation, all right. And as asteroids collide with each other, well, what will happen? Well, these asteroids will collide with each other, and stuff gets knocked off. And where does it go? It just goes into orbit around the sun and continues going in orbit around the sun. But it's dust, and over time it gets pulverized into very, very fine dust. So when we look just before dawn, and I think just after sunset too, possibly. You have to be in a very dark area. But the zodiacal light is actually the plane of the solar system being backlit by the sun, being lit by the sun. You can actually see it under certain conditions. And you can actually see this dust in our solar system that are left over. Now, that's a very interesting thing to have discovered, because the zodiacal light in our solar system is really the same thing as what we see when we say look at the the star Vega in the constellation of Lyra. Vega is like 25 light years away, and it has something called a circumstellar disk. And what's that? Well, a circumstellar disk is a disk of debris or planet-making material or asteroids or small dust like our zodiacal light that surrounds the star. Maybe planets will form there someday. Vega is an A star, and an A star is the earliest type that we could expect to see planets. B stars, which come before them, are too hot and too ultraviolet powered. O stars, of course, are right out because they don't even live long enough. They don't survive long enough. After a few 100 million years, they just go boom. And by the way, remember I mentioned Alnitak before, Amanda?
yes.
When I mentioned Alnitak before, Alnitak is an O
That's
star.
in Orion's belt.
That's right, the leftmost star in Orion's belt. Yep. When I mentioned Alnitak before, Alnitak is an O star, but it's also the brightest O star in the sky that you can see. So if you go out now and you look at the leftmost star in Orion's belt, and you'll say, wow, that's the brightest O star in our sky. Of any star that's an O star, that's the brightest one. So it's pretty cool. But it stands to reason, doesn't it? We are in the Orion Spur, as I mentioned, of the galaxy. And the Orion Spur is sort of a little, kind of a backwater, so to speak, from the main spiral arms. We're not even in one of the main spiral arms of the sun, you know. We're in this other little backwater area. However, we still are close to Orion, and we're close to Alnitak, relatively speaking. And being that Alnitak is there, it's going to be bright as an O star. So there'll be one time or another when some future generation is going to witness, as the Chinese astronomers did in 1054 AD, the supernova of a star. And in the constellation of Taurus, these Chinese astronomers witnessed this explosion of a supernova. And now to them, they weren't thinking, oh, it's returning elements to the interstellar medium. Well, of course not. You know, they didn't know anything about interstellar medium enrichment and all that stuff like we do now. But what they did see was this new star in the sky. Not only did they see it at night, they saw it during the day too. That's how bright the supernovas are. And the Crab Nebula is far enough away that you wouldn't expect it to be too bright, but it was. And it was easily visible during the day. And it lasted like that for a few weeks. And then that brightness went down, it was gone. And then many centuries later, when we pointed our telescopes in that region, we saw the nebula. And that Crab Nebula it's called a crab because it kind of looks like a crab, is the supernova remnant left over from the star that exploded that the Chinese saw. The thing about that is we've had about 100 years to observe it and photograph it. Do you think it stayed the same, Amanda?
In how long?
100 years.
I would say it stayed the same.
Well, you may think so. But in 100 years, believe it or not, we can actually see a tremendous amount of expansion that occurred within that supernova remnant. Believe it or not. And so, see, the universe, when we look out there, we're used to the stars being in the same place. We're used to the sky looking the same. But everything is moving. Everything's in motion. Our sun goes once around the galaxy every 230 plus million years. We've done it 19 and a half times since the Earth was formed. And we always have different neighbors as we do. We don't always have, Orion nearby. We don't always have other things, these other stars around here. We don't always have the Big Dipper. That's a recent development. So, we have a universe that is full of new things always moving, and nothing ever sits still. So I'm hoping that as we move forward here with SkyTour Radio, that eventually we'll be able to share with you even more things that we learn about the universe. But do give a chance, if you can, to go take a look at the SkyTour live stream website and check out the SkyTour live streams Science of the Universe video, and let me know what you think. So I just want to say, for Amanda and I here at SkyTour Radio, I want to thank you for listening to us tonight, and we will see you next time. So keep looking up.